All right, 1.4, polynomial functions. All right, so a polynomial function has any function equivalent to this form, and so each one has a leading coefficient and a degree power, and so on this one, if I have this p of x thing, all right, our polynomial function, my leading term on this one is a sub n x sub n, and so my degree would be power of what? N, and then the leading coefficient is this a sub n. All right, it's that term out in front. And I think you'll be able to really tell, because you've been doing this for a long time, on these examples. So example 1. I think this is kind of backwards. So I'm going to ask the degree first and then the leading coefficient. All right, and so what's the highest degree on A? 4. So we got a degree 4, and my leading coefficient is what? 3. And then on part B, what's my degree on this one? 3, even though it's not first. Is everybody following me on this? Okay, you have to put in that standard form, so descending power of things. And then what's my leading coefficient? -7. And then how about C? What's my degree on C?
1.
No. It's 0. Because this is technically like x to the power of 0. Most numbers, okay, excluding like 0 and infinity, because infinity is not even a number, it's a concept, it's a direction. So like 2 to the power of 0 is actually what? 1. And so this is actually a 0 degree. And so what's my leading coefficient still? 4. All right. Pretty good on those? Cool. All right. Let's talk about extrema. I need a good reader up in here. Thank you so much for volunteering, Miranda. Thank you. Oh, we're on extrema.
The extreme of a graph are the minimums and maximums of the function. There are
2 types. All right. And those are relative and sometimes also known as local extrema. And then we'll have absolute extrema. Sometimes we call them global. More often than not, we call them relative and absolute. But let's figure out what's what. All right. So let's talk about relative extrema first. All right. Trace is going to read in here.
For relative?
Yeah.
Relative extrema local. A polynomial has relative minimum or relative maximum where it switches between decreasing and increasing.
All right, stop there. All right. And so it switches from decreasing to increasing, or it can also switch from increasing to decreasing. All right. And so that's what we're talking about for relative extrema. And then here's another addition part. So keep going.
Or at an endpoint if the polynomial has a restricted domain.
All right, beautiful. So let's look at this example here. All right. So I kind of think of it as like the hills and valleys of the function. All right. And so what is my minimum points of this function? What is my very minimum point of these functions? Right here, right? And so what's this part? At x equals what? 0. And so by true definition, it's where it switches from decreasing to increasing. All right? Do you see how it's switching from decreasing to increasing here? And so that's where we have a relative minimum. And then this is different. It says, or at an endpoint. All right? And so we also have a local minimum right here. And that's at x equals what? -4. All right? And now let's do local maximum. So this is like the top of the hills or at the endpoints. And so where might I have a maximum? At -2, x equals -2, and at +3. All right? And so those are relative extremas. All right?
Of all local maxima, the greatest is called the absolute maximum. The least of all local maxima is called the absolute minimum.
All right, so the very top and the very bottom. All right? And so, do I have an absolute maximum? Do I have a very top of this function? Yeah. What x value was it? It was at 3, right? It was at x equals 3. But then we need to actually find the y value of it. So what is the maximum? 2. So the maximum is actually 2 at x equals 3. All right. Now, does this have an absolute minimum? No. Trace, why is it no?
Because it's open-ended.
Because it's open-ended. What does this keep doing? You see how an arrow? It keeps going down forever and ever. So, does it actually have an absolute minimum? No, it has none. All right. Pretty good? Cool. We're moving. All right, so let's look at example 2 now. All right, so we're going to do the same thing with extrema here. All right, so does it have any relative minima? Does it have any relative minimums? No, it doesn't have any relative minimums. All right, so we got none there. And then, why is it? Relative maximum. Does it have a relative maximum? Yes, at x equals what? At x equals 1. All right. Does it have an absolute minimum? No, it doesn't, because it keeps going down forever and ever. All right, does it have an absolute maximum? Yes. What absolute maximum, where is it at? It's 3 at x equals 1. Beautiful. All right, I'd like you to try B and C on your own. Ella, what we got? What is our relative minimum at x equals what? -2. At x equals -2, right there. All right, does it have a relative maximum?
Positive 3.
At x equals 3. What else?
There's no absolute minimum.
It also has another relative maximum. Where's the other relative maximum? Anybody? At x equals -4. All right? Because it actually includes endpoints. I know this is weird, but let's go with it. We have to do it. All right? Now, does it have any absolute minimums? No, it's got nothing. All right? Because it keeps on going down forever and ever. All right? And then, does it have any absolute maximums? 2 at x equals 3. Beautiful. All right. Call on somebody. Miranda, help me out.
Relative minimum is x equals -3.
And 3. Beautiful. All right. What else we got? Relative max?
At 0 and 5.
At 0 and 5. And?
-4.
And -4. All right. All right. And then, does it have any absolute minimums?
Yeah, -3 at x equals -3.
Good. All right. And then, does it have any absolute maximums?
4 at x equals 5.
Beautiful. All right. All right. So now let's talk about some fill in the blanks, and I'm going to kind of explain things as we go. So between two real zeros of a polynomial, there must be at least one relative or local minimum or relative or local maximum. And I want to kind of break it down. A 0 is where you cross the x-axis. Yes? Yes. All right. And so if you have two real zeros of a polynomial, you're going to cross and you're going to have a max or a min. All right. It doesn't have to go up that way. It could go down like that. Does everybody make sense of this? All right. So what goes up must come down, or what goes down must come up if they're both zeros. Does that make sense? All right, so that's what that one's saying. All right, number 2, polynomials of an even degree. An even degree must have either an absolute max or an absolute min. And here's what I mean by that. An even degree, if you're talking about an even degree, you're talking about like an x squared or an x to the 4th or an x cubed or an x to the 5th or 6th, I mean. All right, an even degree. All right, so what does an x squared look like? Show me with your hand. Show me with your hand. What's an x squared look like? Beautiful, right there, love it. All right, and so if it's an even degree, that's an x squared. That has an absolute what? That has an absolute minimum. All right, does that one have an absolute max though? No. All right, because it starts up, ends up. However, if it's like a negative x to the 6th, all right, it might have something like that. And then what does that one have? That one has absolute maxes, all right? Because an even degree starts and ends at the same spot. It either ends up, starts up, and ends down, and it starts down. But that's what that one's talking about, all right? All right, now let's put some words on what we've already done. So point of inflection. We kind of talked a little bit about points of inflection, but we kind of wrapped around it. All right. And so let's talk about points of inflection. Who read that last? Miranda, pick somebody.
A point of inflection occurs when a function changes from concave up to concave down, or from concave down to concave up.
Keep going.
At a point of inflection, the rate of change of a function changes from increasing to decreasing, or from decreasing to increasing.
Exactly. All right. The way that I like to refer to as points of inflection is there's a change in concavity. All right. And this is just another way to say that second line. The rate of change is increasing to decreasing or decreasing to increasing because that deals with the second. All right. So that's the second rate of change. All right. So there we go. All right. So let's look at this example. So we need to find any values of x where g has a point of inflection. Well, does g change concavity on this function? Yes. Where? Not -2. Not there. But what? At x equals -1. And where else? X equals 1. Those are where my points of inflection are. Because right here, I'm concave what? Up. And then right here, I'm concave down. And right here, I'm concave up again. All right? And so the point in which it changes concavity is called a point of inflection. It took me years to figure this out, but watch this. I call them poise because it's point of inflection. And guess what they start with for poi? It's the first 3 letters of point. Took me years. All right? All right, so on this interval, we need to find the rate of change being increasing or decreasing. All right, so is the rate of change being increasing or decreasing on these intervals? So from 3 to 4, is my rate of change increasing or decreasing? Increasing. It's increasing. So my rate of change is increasing. Tell me why. Concave up. Love it. All right. How about this next one? -4 to -3. What's my rate of change?
Decreasing.
-4 to -3. What's my rate of change right there? It's increasing. Tell me why. Concave up. All right. All right, 10. What's my rate of change doing on -1 to 1? My rate of change is, I can't say going down, but rate of change is decreasing. Because why? Concave down. Love it. And then call on a brother. Call on somebody. Who you got? David. 1 to 2. What am I doing? What's my rate of change doing on 1 to 2? No. My rate of change is doing what? It's increasing. Tell me why. It's concave up. All right. Of course. Ready, Mary? Go.
For 0, less than t, or equal to 3, the number of cars in a parking lot at time t hours can be modeled by the function c t
Equals that. Yep.
-1.
Yes, that. Based on this?
Based on this model, at what time t does this number of cars in the parking lot change increasing?
All right, so what are we trying to find? Before we do anything with our calculator, what are we trying to find? Changes from increasing to decreasing. What are we trying to find? No, it's not switching concavity. It doesn't say rate of change is increasing to decreasing. It just says the function is changing from increasing to decreasing. What are we trying to find? A maximum. We are trying to find a maximum. All right, that is what we're trying to find. And we just got that from the reading. All right, and so we need to put this in our calculator to see where it might have a maximum. All right, so let's go. We all have a graph that kind of looks like this. All right, and so we need to figure out where it changes from increasing to decreasing, which is basically a what? A maximum. All right, and so really I'm trying to find out where the top of this little graph is right here. All right, and so I can't see the top of it. Does that bother anybody? That bothers people? Okay, so let's go to this. So go to window, and really we should change our x inputs. So you see how it says x min? So I want you to press 0 there. And x max, I want you to press in 3. Okay? And the reason we did that is because my domain says it's from 0 to 3. Okay? So we're going to change up this whole window. And then, if you go to y max, because I need my maximum to be bigger, because it didn't fit on my graph yet. Okay? And so let's press in 20. Let's see if that works. I hope it does. All right? And then let's press graph. All right? So y max will have 20. And maybe it will fit now. Oh man, it didn't. That's all right.
Wait, y max is 20?
All right. That's what I did. It still didn't fit. All right. But we'll be all right. We'll be all right. All right. So there's my window now. All right. But it still didn't fit. And that's fine. So now we still need to figure out that value when it's up top. All right. And so we're going to do another calculation. So we're going to press in second, calculate. And before we just use the trace feature, which we're fine with, but now I want to be exact. So what do we want to try to find? You see how it says value 0, minimum, maximum, intersect, dy dx integral thing? Second, calculate. So second, and then the trace button. Press maximum. And what does it say? Look at your calculator. What does it ask for? And so we went from the left and we went from the right, and then our output, it said our maximum was 2.4456. All right? And so we end up having at x equals, or t equals, 2.4456. All right? And so that's the time in which it will have that many cars having its maximum. All right? All right.